Hello everyone, my name is Feng. I will report our paper, MechCircuit, Augmenting laser cut objects with integrated electronics, mechanical structures, and magnets. In this work, we propose MechCircuit, a design and fabrication pipeline for making mechanical-electronical objects with laser cutting. We leverage the neodymium magnet's nature of magnetism and conductivity to integrate electronics and mechanical structure joints into prototypes. We propose a set of basic mechanical structural units to inspire users to create unique and more complex structures. We also propose a set of fabrication pipeline. Firstly, design laser cutting stretch in our software and cut out the components by using the laser cutting machine. Secondly, spray conductive silver ink on the components. Thirdly, embedded magnets and electronic components into the components. Finally, assemble all the components together and the prototype is achieved. More recently, personal fabrication tools such as laser cutters and 3D printers have made fabricating objects more accessible. Researchers have explored converting static fabricated artifacts into simple mechanisms that allows for certain degrees of movement. Other works embedded electronical functions in prototypes to make them interactive. It can be achieved by generating electronical circuits. With a growing interest in interactive prototypes, novel solutions are required to integrate electronic circuits and transformable structures. There are already researchers who have implemented interactive objects with transformable structures by means of folding structures and elastic structures. In HCI, magnets have been widely used for haptic interaction and functional physical input. Outside of the HCI domain, researchers have produced materials by combining conductive and magnetic materials, which are both conductive and magnetic. Our work uses commercially available neodymium magnets. These magnets are both magnetic and conductive and can be used to create circuits with magnetic properties. Next, we will introduce the basic principles of MechCircuits. By using conductive magnets, we bridge mechanical structures and electronic circuits with neodymium magnets, which are the strongest type of permanent magnets available commercially and achieve high conductivity with a plate of nickel and copper. Magnetism enables different components to attach to form mechanical structures and be transformable. Conductivity makes magnets connect electronic circuits. We propose a set of basic mechanical structural units to inspire users to create unique and more complex structures. These basic mechanical-electronic function structures include infinite rotation structure, linear motion structure, polar rotation structure, pressing structure, and rotation linear conversion structure. To determine the technical parameters of the pipeline, we deployed evaluations as a reference for choosing the specific parameters of the conductive path and the salt composition. For determining the parameter of the conductive path, the path resistance with different spray times and different weights was assessed. For the path width, we finally chose to spray the conductive ink 3 times for the least manual operations while having low and stable resistance. For determining the path width, we cut 11 paths with a width ranging from 1 mm to 3 mm on a piece of PMMA. We choose 2 mm as the width for the paths have low resistance and small width. For exploring the compensation parameters for PMMA holding magnets and electronic components type, we use the force gauge to measure the force needed to push magnets and electronic components out of the slot. In this paper, the size of the slot was offset 0.11 mm for the corresponding magnets and electronic components. Besides, to demonstrate the practical feasibility of our fabrication pipeline, we made the empirical evaluation of the MechCircuit performance, which consists of electronical connection quality and magnetically connected structure stability. The results show that the circuit connection quality is independent of the mechanical movement, and we report the force of separating magnetic connected structures. In addition, to evaluate how MechCircuit meets our objective in practice, we held a workshop focusing on the designer's experience of using the pipeline and their perceptions of the method. 8 testers were observed and interviewed. They made positive comments about MechCircuit and gave valuable suggestions. Here are some applications of our output from the workshop. This is a rotatable switch-controlled lamp, When the user touches the wave pattern on the PMMA stand, the LED lights up. We create this prototype to present an example of our fabrication pipeline in our workshop. This prototype demonstrates a working robot that traces the proximate hand. Combining chips resistors, they spread two big electrodes to detect the proximity of the hand. When one hand approaches one side, the robot would work towards it until this hand disappears or gets out of detective distance. This is a lamp with a polar rotation structure and a linear structure. Users can slide the switch cover on the slide switch column to control the brightness of the light. Users can also rotate the switch cover to control the color of the light. There is an interactive panel using 7 press structures. When the user presses the button, the two repulsive magnets touch each other. At this time, the circuit is connected and then the music is played. In this paper, magnets are used to make multiple components attached together. Due to the magnetic connection, the MechCircuit prototype can be disassembled on the heavy force. Since the connection strength relates to the magnetic force, magnets with greater magnetic force can be used to create prototypes that need greater load-bearing capacity. In our circuit path, magnets and electronic components are fixed tight with the salt composition. However, the composition parameters will need to be adjusted when using different thickness layers or materials. Compared with the traditional copper wire, these circuit paths have higher resistance. The circuit resistance limits the use of higher power appliances and dissipates more heat than traditional electronic circuits. In addition, the magnets and the spread circuit paths are directly exposed, which has potential risks in the higher power equipment. Automatic and semi-manual process that is not fully automated. In the future, we will try to use new equipment to enhance the automation. In conclusion, this paper has presented MechCircuit, a design and fabrication pipeline. We further deploy a series of evaluations to determine the technical parameters and demonstrate the practical feasibility of our fabrication pipeline. Besides, we organize a workshop with 8 participants to confirm the creative utility of interactive prototypes and produce a series of applications. We expect that MechCircuit can be used in the product design interaction for a wide audience using the standard laser cutting technology. Please see the paper for more details. Thank you.